Ok. Bonjour, merci d'être venu. Welcome. Thank you for coming. So, yeah, we sort of mixed up the class last time, but I think it's better to do it this way. Actually, I should have thought about this. Even if the notes are written this way, I think in the class it's better to speak. Salut, Nicolas. So, today, our main goal is to uh, derive this equation, which is the next step. Sort of we improve the self-energy. In the same way, when we did RPA, you remember, we is this light too bright? Is it okay? So when we did the RPA, we first started by taking a self-energy that was equal to this and put it there, and that gave us RPA. And then we figured out that, okay, this is nice to take functional derivatives, but then if we try to use only R3 it gave ridiculous results. So we said, okay, let's improve the self-energy. Now that we have the collective modes, we can improve the self-energy, and that gives us screening. So it's the same way of thinking that we are doing now. We in the first step, we did some, we derived this equation by assuming that this is R3 if the point 2 is different from point 1. And then when 2 is equal to 1 plus, so when we have n down and up, then we should get the exact result. So we put a prefactor in front that was just this. And when we looked at the vertex for the spin and the charge fluctuations that are given by this, we found that basically U spin was equal to this. U charge was too complicated, but we decided that we just work with the sum rules and make sure that the Pauli principle is satisfied by working with the sum rule. And that gave us some nice results for the fluctuations. Okay. So are there questions on that? Okay. So now the point is that we want to put in this right there, we want to put basically U spin and U charge. I'm sorry, we did already. It's here that we want to put U spin and U charge and get to sort of some improved relation for the self-energy. So if you look at this, you see it's as if we have a contribution, the self-energy, this expression, you see G of K plus K, Q, and we have a chi spin of Q. So it's as if we emit a virtual spin fluctuations and reabsorb it. And then the vertex is renormalized by, I mean, it's the vertex that corresponds to the spin fluctuation. And similarly, we have the charge. And then we have the corresponding vertex for the charge. So if we were doing Feynman diagrams, what would happen is that we would want to have vertex corrections. So for example, this is an example of a vertex correction. And then the vertex corrections, they go on one side only, because they can always be pushed to the other side. It's completely symmetrical, and we don't want to do double counting. So it's normal to have vertex corrections on just one side. You see, the other side is the bare U. So here is the bare U. And here we have this the spin and the charge of fluctuation. So I can show you that this formula works well. We start with this. So I will share my screen. So you see on the left is the single particle spectral weight, so A of k and omega. And at various points, it's computed by Monte Carlo in a regime where we know that that's the exact result, essentially. So the temperature is pretty high here. It's beta equals 5, so it's 0.2 in units of hopping. So this is the Auburn model at affinning for u equals 4. And so this spectral weight here is for this point 0, excuse me, you see 0. Then we go to a couple more points here, and we finally get to 0 pi. So 0 pi here, it becomes a double peak. So we've lost the Fermi liquid, right? The Fermi liquid, we should have just one peak at the Fermi surface. So I'll show you why this happens. We already know that at beta equals 5, the correlation length starts to be large. So this is a clue, the antiferromagnetic correlation length. So, and then we go to this, and then etc. So as we move along this line here, we stay with this open pseudo gap. And then when we get these 2 points, this moves to lower energy. And if you look at TPSC, calculated with this, the U spin, the U charge, and this formula I gave you, you see that it works pretty well. I mean, you compare this with this, this with that, this with this, and there's even a little peak here, and we get a little peak here. So here, when we get this pseudo gap, that's another thing I would discuss today. When we get the pseudo gap, this is sharper than this, but still qualitatively it's not bad. And then you see this peak is moved back here, and then it's back there. So you see the agreement is essentially perfect. Okay, so it's worthwhile to try to understand where this formula comes from. So let's go back to this. You see that this I can write as minus u times the functional derivative of g. So g12, you see at g12 here, g12, and for spin sigma. So I have a single spin index instead of having 2. Usually the spin indices were with the 1 and the 2, but now I just put 1 because they are the same here. And if I functionally differentiate with respect to phi minus sigma 1 plus 1, I get this term, okay? And then I need to subtract, when I do this functional derivative, it influences, I mean, the z in the denominator is also differentiated. So I need to get only this, I need to subtract g minus sigma 1 plus 1 and g sigma 1, 2. Okay. Now, now what we do to get the self-energy, we multiply by g minus 1. Okay, so if I multiply this whole thing by, so I have g sigma of 1 bar 2. So I will make 2 bar and g sigma minus 1 of 2 bar 2. So then what happens is that for this, you see that what happened, I would get sigma, so this second level of approximation, slightly improved, sigma of 1, 2 will be equal to the minus sign drops out. It's equal to u g minus sigma of 1 plus 1. Okay, so this piece here is the R3 piece, and I get delta 1 minus 2. There, that's the R3 piece that we have already seen. Now here when I multiply by g minus 1, what I have is delta g delta phi g minus 1. But we know that this is equal to minus g delta g minus 1 delta phi, right? This comes from this. Okay? So, so I have minus, so it's plus. So this piece is, so I said minus plus, so this piece is plus u times, whoops, not too fast, u times g 1 minus 3 bar times delta g minus 1 sigma of 3 bar 2 delta phi minus sigma of 1 plus 1. Now, g minus 1 is right there. But you see, it's the same spin here, sigma. So when I functionally differentiate, I get nothing from the functional derivative of this. I get just something from the functional derivative of sigma. And there's an extra minus sign. So this I can write as so I had already plus, sorry, no, okay, that's fine. Now, so this is minus delta sigma of spin sigma of 3 bar 2 delta phi. So as usual here, I need to use the chain rule. So if I use the chain rule, I will get delta g of sigma bar. I have to sum over all the possible sigmas of 4 bar, 5 bar, delta g sigma of 4 bar, 5 bar, functionally differentiated with respect to phi minus sigma of 1 plus. Okay. And now the idea you see is to, for this, I want to use this U spin and U charge. Okay, that's the idea. So U spin and U charge are local. So local means that 3 bar will be equal to 2, and I will be a delta function of 3 bar 2, delta function of 3 bar 4, a delta function of 2 5 bar. So this here will be, so in the end, you see, I will get G sigma of 1 3 bar, some mess here that I'm going to work, and then I get delta G of sigma bar of 3 bar 3 bar 3 bar, because this is all delta function, and delta phi minus sigma 1, it's 1 plus 1, not 1 1 plus 1 plus 1. So what I want to show you, so here there will be some U spin, U charge. What I want to show is that you see I have a G1 3 bar, and then this is like a charge or a spin fluctuation depending on where I'm looking at, but this is a 3 bar 1, okay? 1 3 bar 3 bar 1. So I have a G of 1 3 bar and some susceptibility of 3 bar 1. So when I take a Fourier transform, this is a convolution. So that's why we have G of K plus Q and Chi of Q. Okay? That's all I wanted to show here with this this little thing. Now, now we will just work on these things. So I think I can erase this. So there was the G minus 1 here. And we got rid of this, and then we got G minus 1, and then we changed for this. Okay. So okay, you have some questions? Everything is going smoothly? I'm almost finished. So here there are two contributions, you see. There is delta sigma, sigma delta G, sigma, so same spin, times delta G, sigma, and delta phi minus sigma. Okay. So this piece here is equal to, okay, if I compare with this, you see that to get the same up, what I need to do is to take 1/2 of U charge minus U spin. Okay, given this is just 1/2 U charge minus U spin. Now, what is this? This is 1/4 of chi charge minus chi spin. Okay, why is that? It's because you see these are the chi charge is basically n up plus n up and down, plus the same with the spins the reverse, and the chi spin is and up minus and up and down, plus etc. So if I want these are opposite spins, so it's really this piece that I want here, and it comes in twice in the charge, because when both spins are flipped, it's the same. And it comes twice in the spin, but with opposite sign. So I take chi charge minus chi spin and I divide by 4. Okay. And then we have just one more to do. So this piece here gives the arc refractor. Okay, so it's going to disappear. So the other piece with the opposite spins is delta sigma sigma delta G minus sigma delta G minus sigma delta phi minus sigma. Okay, so now I want the I want only this piece. So that will be 1/2 of so this piece. I'm sorry, it's this piece I want. Huh? So it will be U spin plus U charge, and here are the spins are the same. So if you look at what I wrote earlier, it will be 1/4 of chi charge plus chi spin. Okay. So you see, we are just working on that piece here. And we know that this will give something like U spin chi spin, U charge chi charge. Okay. So what happens when I add, because you see I need, whoops, I erased it, but I need to add these two pieces, the one with the spins the same and the one with the spins different. So I need to add these two. So what will happen? If I add these two, I will have that the cross terms, you see, that are U spin chi charge, they come here with a minus sign, they come here with a plus sign. And this comes with minus sign and with a plus sign here. So the cross terms will survive, will disappear. So it's only this times this and this times this that survives. You spin this times this and this times this. So the final result is 1/4 U spin chi spin plus 1/4 U charge chi charge. Okay, so where did I make a mistake? Because I have 3/8 and 1/8. Well, it turns out that this approximate, I tell you where this comes from, and it's rather subtle. And if you use this, actually, it's not bad. And what is this internal accuracy check? This internal accuracy check is that if I multiply this by G, okay, the G at the first, the G that I was using from the beginning that goes in the chi 0 and so on, which is basically the non-interacting G. If I multiply G by sigma and I integrate over K, so here I will get another chi 0. And if you work it out using the sum rules, you find that, when 1 is equal to 2, you can integrate over 1 because it's translationally invariant. So 1 equals to 2, you see you get an up and down. So if you multiply by G at the first level of approximation, that is a non-interacting G with sigma 2, and you integrate over K, is the same as summing over 1. It's a trace. you use the sum rules and you recover u and up and down. So that's very nice. I mean, it means that this approximation that you did at the second level of approximation is consistent with what you had with the spin and charge fluctuation. I won't show this. It's a little bit of algebra, but you can trust me that it works out. But now what the real sum rule is that I should have G, which has I should have the G that has the same self-energy in it. So if you do that, if you take the G with that self-energy and then you do the trace, then you have to do it numerically. And you find that there's a slight difference with the U and up and down that you computed at the first time. Okay, you see, so I will live with that. And then that's an internal accuracy check in the sense that when both results start to become very different, you know that theory breaks down. Okay. So that's a check on the limit of validity of the theory. Okay. And this 1/4 satisfies what I just told you, that if I multiply by G and I trace, I get U and up and down that I obtained at the first place. So that's a nice check. But this works out also. I mean, if I take this, I multiply by G at the G0, I integrate over K, I get again U and up and down that I obtain.
So
okay, so what is
in what case didn't you get the n up and down that you had in the first place?
When I use the Green's function that has this self-energy in the denominator. So if I take 1 over I omega IQ
You're out of frame right now.
Yes, I'm out of the frame. Huh? I mean, I don't need to write it down. I just use if I use the Green's function.
So if I understand right, it works with G0.
G in it, then it doesn't work out.
Okay, but it's only working with G0.
It's only working
for the two case. For the two case with the 1/4 and 3/8. So for the two cases.
No, for the two cases, it's the same thing.
Okay, right.
Whether I have this or I have this, it's exactly the same thing. When I multiply by G0, the trace is equal to U and up and down. It works in the two cases. You'll understand why it works in the two cases in a second. But if I multiply by the G that has the self-energy in it, the sigma 2, then it's not exactly equal. There's a difference. And you can use that difference as a check on the limit of validity of the theory. Okay? So, you see, when I said that here, this is obtained by taking the functional derivative of sigma, of G sigma 1, 2 with respect to phi minus sigma 1 plus 1. I was working in the so-called longitudinal channel, where I get an up, minus, and down for the spin, and I get the charge. But there's another way to get this function. I could take this Green's function, G of minus sigma of 1, 2. Remember that when I was working with this formalism, there's nothing that forces me to have the same spins here. So the formalism works out even if the spins are different here. If I have spin minus sigma for coordinate 1 and spin sigma for coordinate 2. In other words, then what happens is that this phi, if I have 2 indices here, then I have 2 indices here with this phi. So I could have worked in this transverse channel. If I had done that, if I had worked out all the details, and actually it's a little bit more messy, even more messy. This is already messy. The rest is even more messy. If I had worked out in this transverse channel, the result I would have obtained here is 1/2. Instead of 1/4 this plus 1/4 the other one. And this also satisfies the sum rule. In fact, if I take this term by itself, the way it's written down, this way, this one satisfies the sum rule. I mean, this, you know, this internal accuracy. If I multiply by G and sigma and take the trace, it's equal to U and up. So let me, just to be not too confusing, let me call this consistency between the one and the two particle quantity. Okay. So this consistency between the one and the two particle quantity is, if I used only this term, I get 1/4 of U and up and down. And with this, I get 3/4 of N up and down. And if I get this, if I use this only, I get N up and down. Now, I show you why the reason it's a little bit better to use this is that it is obtained by taking the average between this result and the result I obtained before. So the 1/4, 1/4. So I divide by 2, so this is 1/8. And then this I divide by 2 is 1/4, and I add the two results, and that gives me this. I get 1/8 the spin times the spin thing plus 1/8 times the spin thing, because I divide by 2, and this I get if I divide by 2, I get 1/4, and 1/4 plus 1/8 is 3/8, and here I get 1/8. Okay, so I've taken just the arithmetic average between this result and the other result. Okay. Okay, now I show you why. This is an approximation, but I try to show you. We have checked that numerically it works better, but I will try to show you why it does that. And then the rest will be a little bit more physics. I mean, this is really a lot of formalism, but for the rest of the class, once we get this behind us, we'll do more physics. Okay. So suppose we want to compute a self-energy. Okay, so I have a K plus Q here, which is this. And then I have this bubble here. So Q goes there, then Q comes back here. So I have K prime plus Q here and K prime. Okay. So you see that I should not have. Okay. Let me take. I should have done it the other way, but okay. So you see, in this case, what is happening? What's happening is that if I continue to do this, you see that I'm looking into two particles that scatter each other. So it's as if I'm looking in the particle-particle channel. Okay. And then there is a particle hole channel, which is the one we just looked at, which is to look at this here. Okay, so I have sigma, spin sigma, k plus q. Let me put spin up just to be a little bit clearer. Up, then that interacts with down, and that interacts with up. And okay, so I need another bubble here. So that interacts with down, and then down interacts with up. Okay. So and then we have momentum q that is flowing here. So that was the longitudinal channel for the spin fluctuation. This one here is the particle-particle channel. In other words, I could have also been even crazier. I could have taken a functional derivative of this that has 1, 1 and opposite spin with respect to a field that couples to side dagger. So some off-diagonal field that will be important for superconductivity. And that's this particle-particle channel. Now there's another particle hole channel, and this other particle hole channel is this. So you see, this can be spin up, and this can be spin down. And now, if this is, if I want this to be k plus q, then I will have some k prime and some k prime plus q. But the point is that the momentum that is transferred here will not be q like in this case. It will be some other momentum. And you see, this is again a spin interacting with the spin flip. So if I was looking just at the bubble, it would be that it's as if I go from up here to down, and the operator here that flips from up to down is S minus, and the operator that flips from down to up is S plus. And you know that the expectation value of S minus, S plus, plus, S plus, S minus is equal to, I think there's a factor of 2, Sx squared plus Sy squared. So in a rotationally invariant system, you need to include this other channel here. In fact, they give comparable contributions. We know that this gave us, I showed you a divergent correlation length. So it's certainly some important quantity. And you get it in the two different channels. I would show you the same thing differently to you. So the self-energy is really this. So let me put the k minus q here. And I have the Q that goes there. And I will have K prime minus Q here and K prime. And let me take this as up, and this then will be down. You see what I'm doing here, okay? What I'm doing here is that I'm decomposing this scattering between particles into a particle hole channel. But the more general vertex is this. In other words, you see, if I have two particles that scatter off each other, I can look at this scattering here from many points of view. You see, you see, in this, you have to remember that eventually there will be another thing that comes out here. This is called the Schwinger Dyson equation for the self-energy. And the diagrams I drew before suggest that I can write this in different channels, either particle-particle scattering or particle hole. You see here that would be particle-particle scattering. But if I look at this from this point of view, you see this is like particle hole, because this comes down and this comes up, and then the same. And I could also look at it from this point of view. So this with this, and this with this. And that's another particle hole channel. Okay, so you can see for a general expression like this with two particle in and two particle out, you can look at it from this is one particle hole channel. That's another particle hole channel. And these two is a particle-particle channel. So this general object here, gamma, is a function of Q. If I do this decomposition here, if I look at this, up, down, that's another channel here. You see that was the Q is going through these two lines here. So it's like what I did here. So it's going to, if I look at it from this point of view, so the momentum, net momentum that is transferred is K minus K prime. And then if I look at it from the point of view of this, then it's a particle that is coming in. So this is a function of, no, I have to, sorry, these two. We have two particles coming in and two particles coming out. So this is K plus K prime minus Q. So this general object is a function of all these variables. And when we decompose it this way, we take into account just this one. But clearly the particle hole channel that is the transverse one, by rotational invariance, what I showed you, that S plus S minus is related to Sx squared plus Sy squared, this will have the same singularities as this one. And I have this constraint that this should be equal to U and up and down. So that's why I took 1/2 of the result for this and 1/2 of the result for that, because I have this constraint. It's just an approximation, and you see, because in reality, I need to compute this mess here. I have to let two particles scatter off each other. And we neglect completely this particle-particle channel, which will be important for superconductivity, but for now, it does not contribute. I know this is complicated. Don't worry, I will never ask you rederive this or anything, right? I mean, yeah, it's complicated. So when you go through the notes, you can just derive the 1/4 thing, and that's fine. Okay? You understand? Okay. So what people do now, numerically, when they get the self-energy, let's say from some exact approach that gives them the self-energy, and then they want to understand the physics, what is contributing most to the self-energy? Is this a spin fluctuation, or is this some particle fluctuations? Well, then they do what we just did there. I mean, they write an expression that's valid in the particle-Hole channel, an expression that's valid in the particle-particle channel, and then they see with these approximate results whether they reproduce the exact result or not. You can basically get some insight into the physics. Okay, so let me show you now some plots that we will try to understand. So can we understand this here? Well, we said that there are some what is happening here? Okay, so what's happening here is that in 2 dimensions, if you look at temperature and doping and you fix the value of U, then without the Mermin-Wagner theorem, you would get a phase transition here. And the ground state would be an antiferromagnet. So if here above the Fermi energy, the energy versus K looks like this, and it has a spectral weight as a peak, then when you go to the ground state, then the antiferromagnetism will open up a gap here, because you double the antiferromagnetism is up, down. So you double the unit cell. So this will split like this. So you will get 2 peaks. So this is just a Bragg scattering, because the unit cell has been reduced by a factor, enlarged, by a factor of 2. So the Brillouin zone is reduced by a factor of 2. So here there was no gap, now there is a gap. So how do you go from this to this when there can be no long range order in this finite temperature region? Well, you get this sort of intermediate thing with whoops, what happened? So this is an example in electron dope high temperature superconductors. If you look at the upper quadrant of the Brillouin zone, this is a result from angle resolved photoemission spectroscopy. So if we had a Fermi liquid, we would have just a red line along this here. Instead, you see that we're missing some weight here. So this is the TPSC calculation with using U equals 5.75 and some band parameters that reproduce what's this observed. And then you can look in detail at the energy distribution curves. These are the momentum distribution curves. I will not go into details. I will just try to explain to you why there is this. That will be the last thing the last time to do, I think. So I need to not forget to stop sharing. So So we will start from this, but before, let's think a little bit physically what happened. So let's suppose this is the Brillouin zone, okay? So this is minus pi over A, where A is the lattice spacing, and I will set A equal to 1 very quickly. And this is 0 in the y direction. And then this is that's kx if you want. And you have ky here, okay? And let's suppose that I have a Fermi surface that is, well, let me draw first the Brillouin zone in the antiferromagnetic case. I need to reduce it by a factor of 2 because I have up, down, up, down. So it is, in real space, it's twice as large, so it needs to be twice as small in the Brillouin zone. So that's the antiferromagnetic Brillouin zone. So the spectrum repeats here. I mean, I have the usual periodicity. Okay. Now, assume that the Fermi surface is like this. Then you see that these points here from here to there is related by pi, which is the antiferromagnetic wave vector. So if I have strong fluctuation at the antiferromagnetic wave vector, which is what I showed you last time, then something is going to happen there. And what's going to happen is that the Fermi surface is going to open. What I showed you at the beginning with the Monte Carlo was with the Fermi surface that is exactly, there was no, Fermi surface was exactly the same as the antiferromagnetic Brillouin zone. So the pseudo-gap opened everywhere. But now with a Fermi surface that's closed like that, it will open only in points that are connected by this. Okay, so how does that happen? Let me start with this, and we take this as our, so I will not work out any prefactor or anything. I just know that this will be the most important contribution. Not only that it will be the most important contribution, but it is Q equals pi that will contribute. So if I take sigma at K Fermi, let's say one of these points, as a function of omega, it will scale like, I take only the 0 Matsubara frequency contribution. So here I'm missing a factor of temperature, because this sum over Q is not only over wave vectors, but over Matsubara frequencies also. So I still have the temperature piece. The sum over wave vectors divided by n becomes integral. I will do it in d dimensions, ddq. And then this is almost divergent. So I will write what this approximation that we had the other day. C minus 2 plus q squared. And then I have the Green's function that is 1 over omega plus I eta. I have done the analytic continuation minus epsilon or zeta, because it's measured with respect to the chemical potential. So zeta of K plus big Q plus little q. Remember, because when I write it this way, I have shifted the wave vector around the antiferromagnetic wave vector. So that's why I made this K plus Q here. So if I am at the K Fermi, which is related then this Kf plus Q will also be on the Fermi surface. Okay. Now, if I look at the imaginary part, sigma double prime of K Fermi at 0 frequency, then it will be proportional to T integral d dq of 1 over C minus 2 plus Q square times delta of here so this Kf plus Q is on the Fermi surface. So I can expand near the Fermi because this Q, because of this here, this Q, the Q integral will go down rapidly. So I can write this as Vf dot Q. So but this Vf is the Fermi velocity at this point. So I have Vf, let me define it as Vf prime times Q parallel. So Q parallel, I have a dot product. So the Q parallel is the Q along the Fermi y vector. Then here I can write this as Q parallel square plus Q perpendicular square. I can do the Q parallel integral now. So I'm left with d minus 1 Q perpendicular. And the Q parallel is equal to 0 now. So I just have Q perpendicular. And in doing the integral over Q parallel, I have a V Fermi here. Now I can get rid of this. And now this integral I can do by dimensional analysis, right? So this is proportional to T over Vf. And if I multiply by C square numerator and denominator, I will have Q perpendicular times. I can, well, let me do it completely. I multiply, oops. I'm really running out of space. Integral d minus 1 of Q perpendicular C 1 plus Q perpendicular C square. And if I want this to work out, it means that I have another factor that is equal to Xc to the 1 minus d to cancel this 1 here, and I add the Xc square from multiplying Xc square here and there. So this is Xc to the 3 minus d, right? So you see in 3 dimensions, actually is a marginal dimension, but if we go to 4 dimensions, then when Xc increases, this goes down. So I recover the Fermi liquid. 3 is called a marginal dimension because this exponent goes to 0. But in 2 dimensions, you see the catastrophe. This is just a number, right? So in 2 dimensions, you see the catastrophe that's going to happen. In 2 dimensions, I'm going to get Xc here. Okay. So it means that the imaginary part of the self-energy at 0 frequency, I took 0 frequency here, becomes infinite as Xc grows, instead of going to 0 like a Fermi liquid. Okay. And now, so that's why you get a dip in A of k and omega. Because if I look at A, it's proportional to minus 2 sigma double prime over omega minus zeta k minus sigma prime square plus zeta double prime square. So at the Fermi level, this is 0, and I get 1 over sigma double prime. And sigma double prime is going to infinity. So instead of having a peak at the Fermi level, I have a dip. Okay. And if you want to think of this physically, this quantity T over V Fermi this is, I'm sorry, I'm getting late now. I'm going to finish here. If I look at the uncertainty due to thermal excitations, then this delta E is BF times some uncertainty in wave vector. So if I call this uncertainty in wave vector Xi thermal, it's equal to T. Xi thermal is a thermal de Broglie wavelength. Then you see that Vf over T here is what? Vf over T is the thermal de Broglie wavelength. That's exactly the thing you see when in stat mech when you go from classical to quantum. So Xi over Xi, a thermal. So if you put the units back, this is H bar V Fermi, and K, that's KBT. And then why do we have peaks? Well, the peaks come from the fact that if you're far, if you're at omega far from where the dip is, then you can just replace this by zeta k plus big Q. And you can do this, just gives some integral. And then it has the structure of that we had for the Mott insulator. In other words, this is going to infinity, but not at the Fermi surface, but away from the Fermi surface. So that's that's some k away from the Fermi surface. And when you substitute this here, you will get 2 poles, and that's the 2 peaks that appear. Okay, sorry for this unending talk. So next week we'll go to dynamical mean field theory. I promise we'll finish this. Okay, any questions? Okay, thank you for your patience, and see you next week.
Bye-bye, thank you.
Bye-bye.
Bye.
Bye-bye.
Merci, bonne journée.
Bye.